Transformations of graphs. In this section, we're going to study how certain transformations of a function affect its graph. This will give us a better understanding of how to graph functions. Let's start by introducing the most commonly used basic functions. And let's start by two special types of linear functions. Remember, linear functions are functions that look like y equals mx plus b, right? So linear has to do with the power of x being 1, and the graph of such a function is a line, right? Where m is the slope and b is the y coordinate of the y-intercept. Okay? Alright, so there are two types of linear functions that we are interested in. The first class is the class of constant functions. So a participant in this class is a function that produces an output which is a constant, no matter what the input is. Okay, so let's say f of x is equal to c, where c is a real number. And how do we graph such a function? Well, it's a horizontal line, right? At height c, and let's say that c is positive in this case. If it's negative, obviously the horizontal line becomes below the x-axis, and if it's 0, the pink line, which is the graph of the function f of x equals c here, becomes the x-axis itself. Correct? So let's find the domain and range for such a function. What's the domain of this horizontal line? The domain, in other words, try to flatten or project all the points onto the x-axis. All the points on the graph of the function onto the x-axis, you're going to see the entire x-axis. So the domain is simply all of R, right? So minus infinity to plus infinity. How about the range? The range, remember, the range is by definition the collection of all the possible outputs through the function. Well, this function only produces the output c, right? Again, if you try to flatten the function along the y-axis, you're gonna only see the function, the point c, right? All these points drop onto the y-axis in a perpendicular fashion, all the way to just point c here, right? So the range is just the set consisting of that number c. Okay. All right. So this is one of the linear functions that we are interested in, the constant functions that produce, whose graphs are just horizontal. The identity function, which is the function that's displayed here, it's the function that produces as an output the same as the input. So it identifies the output with the input. So it produces whatever you plug in, you get out. The function does nothing, right? It's a neutral function, it does nothing. Okay, so the graph of this is also linear, right? This is also linear. The slope here is 1, and the y-intercept is 0, 0. The origin, right there. So, and this is the graph, right? Any point here, the output and the input are the same. So any point here has two coordinates, x, x, right? Because the y coordinate is the same as the x coordinate. Over here, any point here looks like x comma c, right? Where x is in the domain, in this case, or real number. So no matter what x is, the output is always c. Over here, the output and the input are the same, right? The output and the input are the same. Okay. All right. So what's the domain of this function? The domain, you project all the points onto the x-axis. You're gonna see the entire x-axis. And similarly, if you project all the points onto the y-axis, or you try to flatten the function along the y-axis, you're gonna see also all of the y-axis. So the domain and the range of this identity function, so the domain and the range are the same. Let's now move on to nonlinear functions. And nonlinear means functions that are not linear. So functions that do not look like y equals mx plus b. Okay, so the power of x is not 1. For example, here the power of x is 2. So this is nonlinear, and this function is called the squaring function the output is produced by just squaring the input, right? X being the input, so the output is just the square of that input. Okay, so the graph of such a function is depicted here in pink. And keep in mind, it's not very accurate, I drew it by hand, but the idea is that the graph is symmetric with respect to the y-axis, okay? And the y values blow up in both directions. So if you input any x, that's the larger x, the larger y. The larger positive x, the larger y, and also the larger negative x, the larger the y. Okay. Recall that any point on this graph is gonna look like x comma f of x, right? And f of x here is x squared. So every point here looks like x comma x squared. For example, 2 comma 4 is a point on this graph, right? 10 comma 100 is another point on the graph. So you see that the y coordinate blows up very fast, right? Okay. Even if you input negative 10, the output is still the square of the negative 10, which is 100. So you're still getting a large positive entity if you input a large negative entity. Okay. Alright, so the domain of such a function, so the domain of such a function is, you can input anything in this function, right? So, because you can always square any number. Squaring means you multiply it by itself. Okay, so in other words, if you try to just project all the points that belong to this graph onto the y-axis, onto the x-axis, you're gonna see all of the x-axis. So the domain is simply all of R, right? How about the range? The range of such a function, this function only produces numbers that are non-negative from 0 onward, right? From 0 onward. Okay. All right. Another prominent nonlinear function is the cubic function that produces an output which is the cube of the input. Okay. So the output is the cube of the input. This function has such a graph. This graph is symmetric with respect to the origin. Any point here has its symmetry with respect to the origin. And recall that any point on this graph looks like, as usual, x comma f of x, but f of x here is x cubed. So x comma x cubed is on this graph, right? For example, 2 comma 8 is on the graph. 5 comma 125 is on the graph, negative 5 comma negative 125 is on the graph, and so on. Okay. The domain of this function, obviously 0, 0 is there, right? 0, 0 is there. So 0 comma 0 cubed, 0, 0 is there. Here also, right? And the squaring function, 0, 0 is part of the graph. And hence 0 is part of the domain and 0 is part of the range. Okay, so over here, the domain. What's the domain of this function? Well, algebraically, you should realize that no matter what you plug in as x, you can always multiply it by itself 3 times. In other words, you can always cube that input. So the domain is all real numbers, right? So you can input anything because you can cube any real number. Pictorially, projecting all those points onto the x-axis yield the entire x-axis. This function is supposed to blow up this way and blow down this way. Okay. Range, the range, this function produces all of the real numbers as outputs, right? Because projecting this graph onto the y-axis, you're going to see the entire y-axis. So the range and the domain of the cubic function are the same. The square root function. So the square root function, that's a function that produces as an output the square root of the input, right? Remember, that's a symbol denoting this, which is x to power half. Okay. So any point here looks like x comma f of x. In this case, f of x is square root of x. And what's the domain of such a function? Well, clearly, algebraically, I cannot plug in a number that's negative, so it should be non-negative, the domain, right? The only thing I can plug in as x, the x sits here, the only thing that can be placed under this umbrella are non-negative entities, right? Okay, and the range, now if you want to look at it pictorially based on the graph, you project all the points, still talking about the domain, project all the points onto the x-axis, you're going to only see the non-negative side of the x-axis. For the range, it's not very different. Any point on this graph has a y-coordinate which is 0 or more, right? 0, 0 is part of the graph, and hence you see a bullet here, you don't see a hole. 0, comma 0, square root of 0 is 0, so 0, comma 0 is part of the graph, and it should be part of the range, and any non-negative number is part of the range, right? So the range and the domain of the squaring function, the square root function, are also the same. Cube root function. So this function produces the third root of the input. Okay, so the third root of the input, so x to the power 1/3. And since this umbrella is odd indexed, I can input any real number, right? So you're gonna see that the domain here is all real numbers. Okay, and the range, according to the graph, the range is also, this is blowing down this way, this is blowing up this way, and everything in between is taken, right? So this function visits all the levels, all the real number levels, and as such the range is going to be all real numbers. Okay, so this function visits all the levels, the y levels, and as such the range is everything. The absolute value function, and we talked about this function before in depth, and we discovered that it had this graph, right? Any point here looks like x comma absolute value of x. It's symmetric with respect to the y-axis. Okay. The domain is all real numbers, correct? All real numbers. And the range, it only produces outputs that are non-negative, 0 or more. Okay. And the last function, the last basic function that we're going to visit is the reciprocal function. It's the function that outputs the reciprocal of the input, or the multiplicative inverse of the input. If x being the input, the output is 1 over that x. Okay. So what's the domain, algebraically speaking, what's the domain of the function? Well, this function produces outputs meaningful entities as long as x is not 0, right? So the domain is everything except 0. So minus infinity to 0 union 0 to plus infinity, which we can also represent it based on set theoretic difference, the set R minus the set 0, right? As we found in the very first video. Okay, so the range, and this is the graph actually. This is how the graph is. And you see that if you plug in 0, meaning if you stand at 0, you look up, you look down, you should not see the function, and this is interpreted here by just saying that the function gets closer and closer to the y-axis, but never reaches the y-axis. Okay, so the understanding here is that no matter how much you zoom in here, the two functions are gonna get closer and closer to each other, but they will never reach each other, and likewise here. Okay, so the y-axis is called a vertical asymptote. Asymptote means the line controls the function. Okay, so eventually you should not distinguish the two just by looking at both of them, right? Just imagine that the two keep getting closer and closer to each other, the line and the function. Eventually you cannot distinguish them except if you zoom in using a computer or something, right? So the line, the vertical line, controls the function, and such a thing is called an asymptote. In this case, it's a vertical asymptote because the line is vertical, the y-axis. So an asymptote is a line that controls the function eventually, in the sense that the distance between the two, the function and the line, shrinks. Okay, and you see if you get closer to 0 from the left, The distance here is gonna shrink, and if you get closer to 0 from the right, this is also shrinking, right? The distance separating the two, the line and the function, is shrinking. Okay, and this happens also at the end behavior of the function. As x increases, if you give me an x that's large in magnitude, meaning large positive or large negative, the output is also very, very close to 0, right? Look at the nature of the output. If you give the function a billion, the output becomes 1 divided by a billion, right? So it's a very small entity yet positive, which means this function decreases, and eventually it's controlled by the line y, the horizontal line y equals 0, which is the x-axis, correct? The distance between the two shrinks. Likewise here, the distance between the two shrinks. Don't forget, any point here on this graph, the pink graph, looks like x comma f of x. In this case, f of x is 1 over x. Okay, so x equals 0, which is the vertical line, as a vertical asymptote, and y equals 0, which is the x-axis, is also an asymptote. In this case, it's a horizontal asymptote. We'll talk more about asymptotes in the future, but just wanted to just introduce them. Okay. All right, so what's the range of this function? Let's zoom in one more time. What's the range of this function? Well, the range is the function outputs everything except 0, right? If you project all the points on the pink graph onto the y-axis, you're gonna see all the y-axis except 0. 0 is not a possible output, correct? The level 0 is not visited by the function. You don't see the function reaching the x-axis, correct? And this is also algebraically can be algebraically discovered. The quotient 1 over x can never be 0, because the only time a quotient is 0 is when the numerator is 0, and the numerator here is a pure constant. It cannot be 0. Okay. All right. So all in all, the range is exactly like the domain. It's all real numbers except 0. Okay. All right. So here's a question. If c is a positive real number, how do we obtain the graph of f of x plus c? So this guy is a function. Let's call it g of x. Okay, so let's give it a name, g of x. So how do we obtain the graph of g of x, which is f of x plus c, and c is a positive number, if we know how to graph the function of f of x? Okay, so let's say that we have the graph of f. Say this is the xy plane. Okay, so, and let's say the function f makes such a dance like this. And the question is, how do you obtain f of x plus c? How do you obtain the function g? Well, if this is the point, let's call it a, according to the picture, this is f of a, right? According to the picture, this height is f of a, right? Because that point right there has coordinates a comma f of a. So this point here has coordinates a comma f of a, because it's on the graph of the function f. Any point on the graph of the function f has the coordinates something from the domain comma f of that thing. Okay. Now for g, what's g of a? What's g of a? Well, according to the recipe of g, g of anything, right? G of anything is f of the thing plus c, correct? So one more time, g of anything, pretend that, I mean, x is a placeholder for the input, right? Let's replace it by a bullet. G of anything is f of the thing plus c, okay? So what's g of a then? Well, g of a is simply then f of a plus c. F of a plus c, correct? And f of a is depicted here by this blue height, this height. That's f of a. Add c to it, and c is a positive number, like 5, 6, whatever. So c is a positive number. Add c to this height, you give yourself g of a. Okay? So go to the picture, measure f of a, which is this, and add c to it, you give yourself that g of a. So, and if you add c to it, so you take f of a and you add c to it. Let's say this is measure c. Okay? So let's color it in pink. So this is, let's say, c. Okay? So this brown in concert with the pink together, that's g of a, right? So that's g of a. This whole thing becomes g of a. Make sense? And then this point whose coordinates are a comma g of a, comma g of a, that's the point that's gonna go, that's gonna belong to the graph of g. Okay? So one more time. If you take a point a and in the domain of the function f, well, first of all, understand that the domain of g and the domain of f are the same, right? Whatever allows f to be meaningful allows g to be meaningful, correct? And vice versa. So the two domains are the same. Let's take a point in the domain of f and hence of g. Apparently this point here is in the domain. And what's f of a? Well, f of a is this height. It was blue, right? So this is f of a. The question is, what's g of a? Well, g of a, according to the recipe, is f of a plus c. So g of a is f of a plus c. And since c is given to be a positive number, so it means that you're gonna add a positive number to f of a. Whatever f of a is, which is this, you're gonna add a constant c. That's, let's say, that's c, the measure c, which was in pink, right? That's the measure c. So you're gonna add to f of a constant c to get the g of a. So g of a is the whole thing then, right? It's c and f of a. Make sense? So this whole thing is g of a. And now, to summarize, this point has coordinates a, which is the x coordinate, comma g of a, which is the height, a comma g of a. And that's the point whose first coordinate is a and belongs to the graph of g. Because any point on the graph of g looks like something comma g of the thing, right? And that thing is in the domain of g. So that point happens to be a. So a comma g of a is going to be in the domain of, and is going to be on the graph of the function g. And that's its location. Now, what's the relationship between this point and this point? It's just a shift upward by c units, right? It's a shift. To get to the point a comma g of a, we shifted the point a comma f of a by c units upward. Make sense? And now, this point a happened to be arbitrarily taken in the domain of the function f. If you do it point by point, it means every point on the graph of f is gonna be shifted upward by c units to get to the corresponding point on the graph of g. So if this point here has first coordinate b, so that point is gonna be b comma f of b, right? Because it's on the graph of f. If you add c to it, if you add the measure c, which is uniform, it's a measure c that's uniform, so this height and this height should be the same. If you add c to it, you got to the point g of b, right? So this whole height is g of b. So this point becomes b comma g of b. Okay? Because this is how the output of g and the output of f are intertwined. G of anything is f of the thing plus c. So g outputs what f used to output, but we add to it, it adds to it that constant c, which is uniform to all inputs, right? So that's what's gonna happen. Since it's gonna happen point by point, the graph of G is gonna be simply a shift of the graph of F upward just by C units. So you're gonna have something like this, okay? With a grain of salt, obviously, but the idea is you're gonna shift the graph of F upward C units. Okay. So this shift is C across the board. Okay, so let's summarize this. So the graph of f of x plus c is obtained by shifting. So it's the shift of the graph of f of x upward at distance of c units, right? At distance of c units, correct? So this is the explanation here. Now what happens if instead of adding we subtract a c? What happens if we subtract the c? Well, you're gonna subtract the c means instead of adding a constant c to the output of the function f to obtain the output of the function g, you're gonna subtract, which means you're gonna go down, right? You're gonna go down. So instead of going upward c units, you're gonna go downward c units. So you're gonna be shifting the function of f downward by c units if you go for minus, correct? So if this is a minus, that's gonna be downward. Okay. All right, so let's do a few examples from the book. That's on page 193 in the book. Let's do number 16. So the question is, use translations to graph the given functions. So the function here is g of x equals square root of x plus 2. Okay, so let's take this problem. So that's on page 193, as we said. Let's do it on the second page. So page 193, and let's do that number, which was number 16. Okay, so g of x is equal to square root of x plus 2, right? So based on what we just found above, the pink statement, if you know how to graph the function f, and you want to graph the function f of x plus a positive entity, you just shift the graph of f upward the distance of c units. Okay, so for this, do we know how to graph the any of the two functions here? Namely, do we know how to graph the function square root of x? Yeah, it's one of those functions that we visited at the beginning of this section. So I'm talking particularly about this one over here. That's the square root function, correct? I mean, the graph looks like this. So I'm gonna carry this knowledge and I'm gonna try to employ it here. Since I know how to graph this guy, now according to the finding that we just discovered above, the pink one, so f of x is gonna be the square root of x plus that constant 2, which is positive. What I'm gonna do is I'm gonna graph the function f, which is the square root, and then shift it upward a distance of c units, and the c happens to be 2 here, right? So if the parent function here is, let's call it parent function, because I know how to graph it. Let's refer to it as parent function, and p for parent is square root of x. The graph of this is simply what we just talked about above. It's simply this one, right? That's the function p of x, which is square root of x. So this guy is p of x, right? This guy is p of x. Now what's g of x? It's p of x plus 2, right? So g of x, which is p of x plus 2, according to the discussion above, is going to be obtained by shifting the graph of p, right? By shifting the graph of p upward a distance of c of 2 units, right? So upward a distance of 2 units. Which means what? Which means what? You take that function p and you shift it upward by 2 units, you obtain that function g. So it's not that bad. So you just create this xy plane, and then the g graph is simply a shift of that function 2 units upward. So you start here instead, and something like this, right? This is the function g of x, and that point here is 2 now, right? That point, the height is 2, 0, 2. It used to be 0, 0. Make sense? I mean, you can check that 0, 2 is part of the graph, because I mean, plug in 0 for x in the function g. Plug in 0. The 0 is gonna sit here, right? So what g is gonna produce for input 0 is the same what p produced for input 0, which is 0, right? Plus 2. And 0 plus 2 is 2. Okay? Alright. Let's do another one. How about now we do 18? So h of x is 1 over x minus 2. So this time around, h of x, this is number 18. H of x is equal 1 over x minus 2. Let me change the color. How about blue? Okay. All right. So who's the parent function that's involved in this game? Who's the parent function who's involved in this game? It's the 1 over x, right? It's the reciprocal function. And we know how to graph the reciprocal function. Correct? So if you go back to that earlier page, let me take you there. So I'm talking about 1 over x, which is this function, the reciprocal function, right? Which has this pink curvature. Okay. So that's the thing I'm gonna label as p of x. That's the thing that I'm gonna label as p of x. It's the parent function that's gonna produce this child h. Okay, so it's 1 over x, and the graph of this is what we just saw on the previous page. So it's gonna be something like this, right? Oops. Let's try it again. So something like this, right? Something like this. So that's the function p of x. It has two asymptotes, one vertical and one horizontal. Let's color them in pink for vertical. That's the vertical asymptote. And let's color the other one in red, which is the x-axis. That's the horizontal asymptote, correct? So that line is y equals 0, and the vertical asymptote is x equals 0. Meaning, as we discussed above, those two lines control the function. For example, the red line controls the end behavior of the function, and the pink line controls the function around 0, right? If you get closer to 0 from the left, the green function is controlled by the line, the pink line, meaning that the distance between the two shrinks. And similarly, if you approach 0 from the right, also the pink line is going to control the green graph, right? Okay, so this is the graph P. So that's P of X. That's P of X. And now how is H related to P, at least algebraically? H is P of X minus 2, correct? So H of X is P of X minus 2. And do we know how to graph P? Yeah, we just graphed it. So how are we gonna graph H? Well, according to what we just discussed above in the pink statement, we're talking about the minus now, right? So if you know how to graph F, in this case, the graph, the function name is P here. If you know how to graph P of X, just shift the graph of P of X downward at distance of C units, wherever this positive constant C that sits here. Correct? So that's exactly what I'm gonna do. So H of X then is obtained by shifting the graph of P of X downward a distance of 2 units. Why 2? Because that's the C guy. And why downward? Because of the presence of this minus, right? Distance of 2 units. So you're gonna go to this pink graph in order to obtain the graph of H. Let's call it the blue graph. You're gonna shift the green graph downward by 2 units. Obviously, the controlling line y equals 0 is gonna also shift down, right? Because that whole picture is gonna be translated down. And as such, that horizontal line is gonna now become at the level y equals -2, right? The controlling line. Okay. All right. So let's do that below. Let's say this is the xy plane. Let me make some room for this graph. Okay. All right, so this is the xy plane. Let's do it like this. Okay. So what you see in green now is gonna be shifted downward 2 units. So this horizontal line y equals 0 is gonna now become, let's say, let me just make it a solid line. That's the line now, which is y equals -2, right? -2. We're shifting it down by 2. We're shifting everything down by 2, so that line is gonna also be shifted down by 2. And the blue graph is gonna now look like this, right? So that's the function h, and that tail is gonna also look like this. So this part is shifted down by 2 units, so now it's this guy, and this portion shifted down by 2 units is gonna also go down like this. Correct? Okay, so the function h crosses the x-axis, right? The function h crosses the x-axis. Am I correct? How about you figure out? How about you try to find those 2 coordinates? Obviously, the y coordinate here is gonna be 0, right? So can you find that intercept? Can you find that x-intercept? How about I leave it as an exercise? So find this x-intercept. Okay? So find it and we'll discuss it in class. Let's now go to question number 2. And it goes like this. If you have a number c that's positive, how do we obtain the graph of f of x plus c? Observe that this is different than what we had before. We used to have f of x plus c like this, right? Which means f is gonna operate on x, it's gonna produce an output, and then we're gonna add c to the output. So it has to do with adding to the y coordinate, correct? This is what we discovered. Over here it's different. What we have here is we're adding to x a constant c, okay? And then f operates. So the timing is different. Here I'm adding to the input x a constant c, and then f is operating on that sum. Make sense? Whereas in the other one, as we said, f of x plus c like this, f acts just on x, produces an output, and then that output is going to be added to c. Okay, so the timing is reversed. Here we add we add c after f produces an output, so it becomes an addition to the y coordinate. Whereas in the purple, I'm adding to the x coordinate, so to the input, and then after I add to the input, f is going to operate. Okay? Alright, so let's see how this is going to be translated at the level of graphs. Let's call this guy again g of x. Let's give it the name g of x. Okay. And let's say that the function f has a graph, let's say like this. Okay. So the question is, there is a relationship between algebraic relationship between the function g and f. The question is, how does this translate at the level of geometry? So how can I actually find the graph of g from the graph of f? Okay. So let's write the recipe. G of x, let's say g of anything, is equal to f of that thing, it's the same x, of that thing, plus c, right? Let's actually color these bullets by pink. Okay, so that bullet is a placeholder for the input. Okay, and let's for example try to find what g produces at 0. Okay, let's try the bullet being 0. So then g of 0 becomes, this is the recipe, right? G of anything is f of the thing plus c. So g of 0 in particular is when the bullet is 0. The bullet is 0, so f of 0 plus c. Okay? And don't forget what this means. This means I'm adding those before f operates. What's c plus 0? It's c, right? So this becomes f of c. And now you can say that g of 0 is equal to f of c. So what does this mean then? G is gonna produce at 0 what f used to produce at c. Okay? Let's say this is c. Let's say that this measure here is c. Let's say this is how much c is. Okay? So again, g at 0 is gonna produce what f produced at c. That's the point c, and that's f of c. And that's f of c, correct? That's f of c. So that's the point whose coordinates are c comma f of c, which belongs to the graph of f. Correct? Now the question is, so what's g of 0? G of 0 is f of c. So g is gonna produce at 0, assuming that 0 is part of the domain of g. So at 0, this is 0, right? At 0, g is gonna produce what f produced at c. This is how much f produced at c, this height. So that height is gonna be produced via g, via the green function, let's say g, but now at 0, right? So g of 0 is, that's g of 0. It's the same height as f of c, right? It's the same height as f of c. So that's g of 0. And that's the point that's gonna correspond to the point c comma f of c, but this point is now on the graph of g and has coordinates 0, g of 0. Correct? So this green thick point corresponds to this blue thick point on the graph of f. This one is on the graph of g. And what do you realize? You realize that the function g produced at time 0 what f produced at time c, right? Which means there is a shift of this point to the left by the amount c. Okay, so if you don't want to just go to point 0, let's say you go to a point A. Let's say this is the point A. Okay, let's say this is the point A, and let's say at this point A, this is how much f of A is. Okay, let's say this is how much f of A is. So at what time or when does g, the function g, produce what f produced at time A? Okay, so what should I plug in here so that I get here f of A? That's my question. At what moment g produced as an output what f produced at the time A? Well, it suffices to replace the bullet by a minus c, right? Let's try it. What's g of a minus c? Who's the bullet? The bullet is a minus c. Let's color this in pink. That's taking the role of the bullet, right? And then that's gonna be equal f of the bullet, which is a minus c. So the bullet, which is a minus c, plus the c, correct? Plus the c. One more time. If you didn't follow, how we discovered the bullet, don't worry about it. Let me just start the discussion by asking you to evaluate g at a minus c. Okay? So g at a minus c is f of that a minus c. It's the same bullet, so a minus c plus the c. And how much is a minus c plus the c? It's a, right? So it's a. So now if you focus just on the leftmost and rightmost entities, this means g of a minus c is equal to f of a, which means g is gonna produce at a minus c what f used to produce at a. If that's a minus c is earlier, right? It comes earlier. So maybe something like this. That's maybe a minus c. It's earlier, right? Because c is a positive entity. So g at a minus c. So what g is going to produce now, right? The green function is going to be found at the same level as the same y level as f, but at time a. Okay, so what is that? So that's the height that I'm going to preserve here. Correct? So that point here has coordinates a minus c, g of a minus c, but g of a minus c is f of a. Correct? That point corresponds to that point. And how are they related? This green point is a shift of that blue point by the amount c, right? So it's a shift by the amount c, but to the left. Am I correct? Okay. So what can you say then, since this is going to happen point by point, no matter what a is? We took the case when a was 0 and we realized that also it's a shift to the left by c units. Since this is going to happen point by point, the green graph, the graph of g, is going to obtain by just shifting the blue graph to the right, to the left by the amount c units, right? So you shift the graph of f to the left by the distance c to obtain the graph of g if g is given by this recipe. Okay, so imagine that f is like a signal function, and G is related to F via this recipe. The question is, what is G then? Well, according to the discussion we just made, G is going to allow you to see C units ahead of time what F allowed you to see, right? So G is going to produce this point, this height, this output, which is at time A minus C now, but through the signal F, it used to produce it at time A. And clearly A minus C comes earlier in time than time A if C is a positive entity. Okay, so G allows you to see C units ahead of time what F allowed you to see before. Okay, so I'm gonna summarize this discussion. So F of X plus C is obtained by shifting the graph of F, right? This is the green graph, and the blue graph is the graph of F. It was obtained by shifting the graph of F to the left a distance of C units. Correct? Why C being a positive entity? Makes sense? So this thing is, the graph of this thing is simply a horizontal shift to the left by the amount C of the graph of F. Okay, as just indicated over here. Now, what if that plus is a minus? So now you subtract by C. Well, if you subtract by C, run the same program. G of the bullet now is F of the bullet minus C, right? This is now is going to be minus. And if this is minus, let me actually put the minus above. If this is now minus, when does this become an A? Well, this becomes an A if you input here instead of this pink bullet, what is it? A plus C, correct? A plus C. So try it. G of A plus C is going to be F of A plus C minus, right? Minus C. And plus C minus C is simply 0. So this becomes F of A, correct? Pay attention. I'm just talking about the red operations. So this means G of A minus C is equal to F of A. So what G is going to produce at time A plus C, and A plus C is over here, right? That's time A plus C. Let me change the font. This is A plus C. That's time A plus C, correct? What G is going to produce at time A plus C is what F produced at time A. That's what F produced at time A. Now this is going to be produced at time A plus C. So the height is going to be over here, right? This output is going to be over here now for the graph G, which is with the minus. So now G is there's going to be a delay in the output for this function G, right? So the shift is going to be to the right this time. Okay? So in terms of signals, the signal G is going to be a delay of the signal F by the amount C units of time. Okay? Because the shift is going to occur now to the right. It's a shift to the right, right? By C. Okay, so the summary of that discussion is F of X minus C is obtained by shifting the graph of F now to the right, a distance of C units. Okay, let's now go and apply this like we discussed, like we applied the previous result. Let's go to the book and pick up a couple of problems. That's on page 193. Let's do now 20. M of X is absolute value of X plus 1. We're gonna use translations to do this. to graph m of x from a parent function, and clearly the parent function that's going to be involved here is the absolute value function. So let's write this down. So that's number 20 on the same page, 193. So number 20, and here I have m of x equals absolute value of x plus 1. Okay, so keep in mind this last result that we had. F of x plus c, right, f acting at x plus c, is obtained by shifting the graph of the function f to the left at distance of c units. And the red here, if the operation is minus, you go to the right. So the parent function that's involved in this game is the absolute value function, which we know how to graph. So let p of x be the absolute value function, whose graph is the V-shaped, right? So something like this. Something like this, right? Okay, so that's the graph p of x. The question now, how do I graph m of x if I know how to graph this? Well, you gotta find an algebraic connection between m and p. And the algebraic connection is, let's see, so m of x. How do you represent m in terms of p if m of x is the absolute value of x plus 1? Well, m of x is the absolute value of x plus 1, and p of anything is the absolute value of the thing, right? Who's the thing here for within the absolute value? It's the x plus 1, correct? So that's the guy that's going to sit as the star in p. So as such, you obtain p of x plus 1. So one more time. M of x, I know the recipe of m of x. It's absolute value of x plus 1. I want to connect it algebraically to p. And then once I connect it algebraically to p, I use one of the earlier results to actually know how this translates at the level of geometry. Well, the algebraic connection is between m of x and p of x. Well, it's the following. Since m of x is the absolute value of x plus 1 and p of x is the absolute value of x, so p of anything is the absolute value of the thing, since I'm talking about absolute value of x plus 1 here, so this guy, x plus 1, should be the input of p, because p outputs the absolute value of the input. If you want the absolute value of x plus 1, that's p of x plus 1, correct? Okay, so m of x is p of x plus 1. Now, we know how to graph p. This is the graph of p. Do we know how to graph p of x plus 1? So if you know how to graph p of x, do you know how to graph p of x plus 1? Yeah, it's simply the graph of p of x plus 1 is obtained by shifting the graph of p of x to the left at distance of c units, correct? This is what we discovered before. So I'm going to use this result then. So this algebraic relationship allows me to conclude that the graph of m is obtained by shifting the parent function p of x, so by shifting the graph of p of x to the right, to the left at distance of 1 unit, right? At distance of 1 unit. This is what we discussed above, and as such, what do we obtain? So you just shift the graph of p 1 unit to the left, and you simply obtain a graph like this. So what used to be the lowest point now is gonna happen here, right? At -1 as opposed to at 0. And then you're gonna have that V shape shifted like this, right? So something like this, okay? Obviously this angle, as we discussed before, this should be 90 degrees here, but anyway, you got the idea, and this is m of x. Okay? So m of x happens to be this function. You can check, look. If you plug in -1 in m, what's m of -1? M of -1, so instead of x you're gonna have -1. It's gonna be absolute value of -1 plus 1. What's -1 plus 1? That's 0. So absolute value of 0 is 0. So m of -1 is 0. Right? It's right there. -1 comma 0. That's the point we're talking about. Make sense? How about m of 0? So at time 0, what's the height? M of 0 is the absolute value of 0 plus 1. 0 plus 1 is 1, so it's the absolute value of 1, which is 1. So that's the height 1 here, right? Which is understood because that used to be at the time, and P, it used to be at time 1, right? It was 1, 1 and P, and M is going to be 0, 1 because you shift that point to the left by 1, right? So it's going to occur at time 0 now. It's right there. At time 0, you have 0, comma 1, right? Okay, so that's number 20. How about now 22? How about this one? T of x is the third root of x minus 2. Okay? So 22. T of x is the third root of t minus 2. Okay? Sorry, x minus 2. My bad. T is the name of the function, and x is the name of the input. So it's the third root of x minus 2. Okay. So who's the parent function that's involved in this? It's the third root, right? And how do we graph the third root? Let's go back to that page. It's right there. That's the graph of the third root. Okay. So I'm gonna use it as a parent function and build on it. Okay, so the parent function is P of x, which is the third root of x, and its graph is the one that we just visited. So something like this, right? That's the parent function P, which is this guy. Now I would like to find T of x. I want to find it algebraically before I conclude geometrically. Okay? If you see it immediately, great, but what if you don't? So how can I connect T of x to P algebraically? Well, T of x is that third root of x minus 2, correct? How can I write this in terms of P? Well, P of anything is the cube root of the thing, right? And who's the thing? Who's sitting under the umbrella now? It's the x minus 2. So the star better be then x minus 2. So that guy is going to be x minus 2. Okay? Hope it makes sense. So, oops. So this is then equal to P of x minus 2. Alright. Now, if you know how to graph the function P, which you do, then you're going to know how to deduce the graph of P of x minus 2. How? Well, we have a result that we just discovered. It's right there with the red part. F of x minus 2, right? So the name is T in this case. T of x minus 2 is obtained by shifting the graph of T of x, actually P, sorry, my bad. So P of x. P of x minus 2 is obtained by shifting the graph of P of x to the right, I'm talking about the red part, to the right a distance of 2 units, correct? So that's the result I need to invoke. So this entails that the graph of t of x, so the graph of t of x, which is p of x minus 2, is obtained by shifting the graph of p to the right a distance of 2 units. Okay, I'm just copying the result, a distance of 2 units. I'm copying the result and that's mentioned above, and obviously just adjusting the name of the function and the amount by which I'm shifting. Alright, so we're gonna take this guy and shift it to the right a distance of 2 units. So what used to be this point now is gonna occur here, right? Okay, so it's not that bad. So we're gonna have something like this. And again, this is gonna be right there at the point 2. It used to be at 0, 0. Now it's gonna be at 2, 0, right? And something like this. So that would be the graph of t of x. Okay? Let's collect now all the results that we discovered so far and place them in a big theorem. So let's call it theorem 1, which was about vertical and horizontal shifts, right? So all the results were about vertical and horizontal shifts. Everything we found before are actually listed here. Let C be a positive real number, then the very first one we found, if you add C to the outputs of the function f, then you are shifting upward the distance of C units. If you subtract from the values of the outputs of f by the amount C, then you are doing a shift downward. If you're adding a positive entity to the input of the function, then you are looking ahead of time, right? You are actually looking C units ahead of time, which means you're shifting the function f to the left a distance of C units. And if you are subtracting a positive entity C from the input, then you are delaying the output to come out. So this means that's gonna be a shift to the right by that amount C. Okay, let's do problems from the book now that actually combine these together. Okay, not just one by itself. How about 24? So same questions, but now 24. Now you have a couple of translations, right? A couple of translations as opposed to one as before. So we have b of x equals absolute value of x minus 2 plus 4. So let's write this down. So that's number 24. So 24, b of x is equal to absolute value of x minus 2 plus 4. Okay. All right. So we're gonna start as usual from a parent function. The parent function here, parent function again, it's a function that you know how to graph, that's gonna allow you to have a baseline from which you're gonna start building that new function b. Okay, so what's that parent function that's involved in this? It's the absolute value function. I mean, you see it's highlighted here, and we know how to graph this function, correct? That function is the V-shaped. So it's something like this. That's P of X. Okay. So what I'm gonna do is I'm gonna cook up B by adding either this guy or this guy at a time. I'm not gonna combine them. I'm gonna do it in steps. If you've seen this concept before, sure, you can combine. But if you haven't, I'm gonna do it in steps. So you choose whichever you wanna do first. If you wanna add the -2 or you wanna add the 4. There's no, I mean, you can do any of the two before the other, okay? So let's say I choose the -2, and let's call this intermediate function I of x, I for intermediate, okay? So it's an intermediate function. It's not the target function B. It's an intermediate one between the parent and the final product. So it's absolute value of x minus 2. I'm gonna build on P to find I, and then I'm gonna build on I to find B. This would be the last step, okay? So this is I of x, this guy, that's I of x. How is I of x related to P of x algebraically? We discussed this earlier. So if P produces the absolute value of the output, of the input, one more time, if P produces the absolute value of the input, and I want the absolute value of x minus 2, so this guy better be, this guy is x minus 2, so that guy better be x minus 2, correct? So this is then algebraically, I of x is simply P of x minus 2. Make sense? So one more time, I of x is absolute value of x minus 2, and absolute value of x minus 2, I want this to be x minus 2, so I want this to be x minus 2, so it becomes P of x minus 2. Okay? And now back to that theorem, which is the collection of all the results that we discovered. Which one is it? Which part is it? 1, 2, 3, 4. Well, we're talking about P of x minus c, so we're talking about the very last one, right? This pink one. How do you obtain P of x minus 2 from the graph of P of x? Well, you just shift the function P of x to the right at distance of 2 units. This should be 2, right? In my context. Okay, so I'm going to shift the graph of P 2 units to the right. Okay, so I'm gonna take the graph of P shifted 2 units to the right, and I'm gonna obtain this one, right? This is the graph of I of x. So this guy used to be at 0, now is gonna be at 2. Correct? Now it's going to be at 2 because we are shifting to the right by 2. So this is 2 now. Okay. Alright, so now I know how to graph I. I'm building towards B, right? What am I still missing in B? I'm still missing the plus 4. So I'm going to, and this is I of x. So B of x is I of x plus 4. Okay? So B of x is this guy, which is I of x plus that 4. Okay? Do we know how to graph I of x? Yeah, it's that guy. That's I of x. So you want to graph now I of x plus 4. Let's go back to those results that we have. Which format is it? I have I of x plus 4. It's the very first, right? So it's of the form, it's that brown statement. I of x plus 4 is obtained by shifting the graph of I of x, which we know how to do it, it was the purple one, upward at distance of 4 units. Okay, so I'm going to go to the graph of I, shift it upward by 4 units to obtain B of x. So I'm going to take the function I, shift it upward by 4 units to obtain that function, that graph of B. Okay? let me just shift that guy a little more. Okay, so I'm shifting I of x upward by 4 units. So that guy is gonna become now here. I'm gonna have these two branches, right? One more time. It's gonna be here. And it's gonna have these two branches. Something like this, right? So what's this point? It used to have an x coordinate 2, so still 2, right? But now we shifted it up by 4, so that height is gonna be 4. So what's this point? That's the point 2 comma 4, right? Okay. And this is the final product b of x, the desired one. Okay. So this is how you can do things step by step. Again, the more you do it, the faster you become. You can see it immediately from the get-go, that this is simply a shift by 2 to the right and by 4 upward. Now if you do it, if you reverse these things, if you add the 4 before the 2, which means you're gonna do the the vertical shift by 4 first, and then you're gonna do the horizontal shift by 2 to the right. So you're gonna get, again, you're gonna go to the same thing at the end of the day. The b function is the same, but instead of having your I like this, you're gonna have your I if you take your intermediate function, let's call it k of x, to be absolute value of x plus 4, so you're shifting the parent function by 4 units, right? So you're shifting the parent function by 4 units. And then, if you want to go to b, you're gonna subtract the input by 2 to actually have x minus 2 here, which means you're gonna take the function k and shift it to the right by 2, right? And obtain the same function b. So it's gonna be the same graph. So my point is, doesn't matter which one you do first, the 2 or adding the negative 2 or adding the 4, as long as you do it correctly, the final product, the final graph is the same. Okay. All right, let's do another one. How about doing 26? So d of x is 1 over x plus 4 minus 1. So 26, d of x is equal to 1 over x plus 4 minus 1. Okay. All right, so before we did the minus 2, now I'm gonna, and we discussed orally the other way, if you go the 4 first and then the 2. What I'm gonna do now, I'm gonna reverse the order that we followed above. I'm gonna do the negative 1 and then I'm gonna follow it by the plus 4. Okay, so you get to see both ways. What's the parent function involved here? It's the reciprocal function. It's the 1 over x function, right? So p of x is 1 over x, which we know how to graph. It's one of the basic functions that we listed at the beginning of this section. Okay. So it looks like this. And this function has two asymptotes, if you remember, two controlling lines. This line here, which is the x equals 0 line, okay, correct? And this line, which is the y equals 0 line. So this is also an asymptote. Okay, so this line y equals 0, and the pink line is x equals 0, right? This should be pink. Okay, all right. So that's 1 over x, that's p of x. So my eye is on D, but I need to cook it one translation or one transformation at a time. Meaning either you inject the minus 1 or you inject the plus 4. Since we did earlier the step adding the 4, that guy first, what I'm going to do now, I'm going to inject this followed by the 4. Okay, so I'm gonna have an intermediate function. Let's give it a name. How about w for this intermediate function? So w of x is gonna be, I'm just gonna inject the -1, okay? So it's gonna be 1 over x minus 1. Okay, so what I'm gonna do is I'm injecting this guy. Alright, so now the question, how is w related to p? Remember, I'm gonna build on p to deduce w, and then once I have my hands on the graph of w, I'm gonna build on w to actually get to the desired 1D. Okay? So w of x is 1 over x minus 1. How does this relate algebraically to p? Well, that guy is p of x. So this is simply p of x minus 1, right? P of x, this guy, minus 1. Okay? And back to theorem 1. So I have the format p of x minus 1. So which format is it? It's the green one, right? P of x minus 1. P of x minus 1 is obtained by shifting the graph of p of x downward a distance of 1 unit. Okay, so I'm gonna take that reciprocal function, and shift it downward by 1 unit. Okay, so shifting it by down unit, we discussed it above. It's gonna amount to shifting that horizontal asymptote down by 1. So you're gonna have, instead of y equals 0 as a controlling line for the end behavior, now we're gonna have y equals -1 as the controlling line. Okay, so that pink line is gonna remain the same. That pink vertical asymptote, and then the horizontal axis now is not a controlling one anymore. Okay, so let me erase it again. That horizontal axis is not a controlling line, because the controlling line now is at the level -1. I'm shifting down by -1. I'm shifting down by 1. So that red line now is at this height, this depth. Okay, y equals -1. And I'm shifting everything down by 1, so the green function now is blue, and it happens to be like this. Correct? Something like this. So that's the function w of x. That's the function w of x. Okay. All right. Now I'm one step away from the final function, which is the d function. I know how to graph w. The only difference between w and d is that +4, right? Look, this is w. This is the recipe of w. The only difference between w and d is that I have a +4 here, correct? All right, so I would like to have a relationship between an algebraic relationship between d and w. And what is the relationship between d and w? So w has, or d has over here x +4, and this guy is the input in w. So who should be this guy then? If this guy is the same as this guy, and then d should be x +4, so this guy better be x +4 then, correct? All right, so d of x, which is 1 over x +4 minus 1, that's what d is, correct? It's right there. That's what d is. I want to connect it algebraically to w, and we just said it. Since this guy downstairs is x +4, and which means this guy should be x +4, and that's the guy that's sitting as an input in w, correct? So that should be x +4 then. Make sense? So what's d of x in terms of w? It's w of x +4. That's the algebraic connection between d and w. D of x is w of x +4. Now, do we know how to graph w of x +4? Well, we know how to graph w of x. We know how to graph w of x. how do we graph w of x plus 4? Well, it's of this format. W of x plus 4 is obtained by shifting the graph of w of x to the left a distance of 4 units. Correct? So I'm going to shift the graph of w to the left by 4 units. So I'm going to take this whole thing, shift it to the left by 4 units. And what do I obtain? This is the xy plane. If you're shifting it to the left, that horizontal asymptote, that controlling horizontal line is not gonna change, right? You're shifting horizontally. It's not gonna change. What's gonna change is the controlling vertical line, right? It's gonna now, you're gonna shift it to the left, to the left by 4 units. So it's gonna become x equals -4. Correct? So the line now is going to be x equals -4. Let's say over here. Let's say this is the line x equals -4. Correct? Because you're shifting that you're shifting everything to the left by 4, so that line becomes here, and the red line remains the same. It's not affected by horizontal shifts, right? It's only affected by vertical shifts. So let's do it properly. That's y equals -1, which used to be y equals -1. And this portion here, this portion of the graph now is gonna be over there, right? So it's gonna be like this, right? This portion, which used to be controlled by the line y equals -1 and the vertical line x equals 0, now it's controlled by y equals -1 and the new vertical line, which is x equals -4. And this upper portion, which is that guy, now is gonna be, it's gonna start here and it's gonna end here. We know that. The question is, where does it cross the x-axis? Well, it crosses the x-axis when x is when this entity, when the output is 0, correct? When the output is 0. So can you figure out where it's gonna cross? I'm gonna give you the right, because you have 3 ways to do it, correct? So this is one way, which means the x coordinate is below 0. Another way to do it is, or another possibility is this crosses the 0, right? And a third one is going like this and coming down like this, so crossing at the positive side. So you have 3 ways. I know it's gonna start here and end here, correct? I know that. But the idea is, where is it gonna cross the x-axis? Is it gonna cross it from the negative side at 0 or from the positive side? So I'll let you figure that out. So come up with a way to actually do it on your own. Find the x-intercept. An alternative way actually is to actually find where D crosses the y-axis. So the y-intercept, which is easier than finding the x-intercept. I still want you to find the x-intercept, but just for the sake of this video, let's find which one of these 3 possibilities, the green, the purple, or that brown thing. Instead of looking at the x-intercept, I can look at the y-intercept. Let's check D of 0. D of 0 is equal to 1 over 0 plus 4, which is 4 minus 1, correct? So D of 0 is 1 over 0 plus 4, so 4 downstairs, minus 1. And 1 over 4 is smaller than 1, so this difference is negative, right? 1 over 4 minus 1 is a negative entity. So D is going to cross the y-axis from the negative side. So we're talking about this point, not this point, nor that one. It's this point. So at the end of the day, it's the brown thing, not the green nor the purple. Okay, so one more time, we had three possibilities. I know that the function starts here and ends here because it's a shift of this guy to the left by 4 units. I know it starts here and ends here. The question is, where does it cross the x-axis? Is it on the positive side, negative side, positive side, or at 0? Instead of looking at the x-intercepts, I looked at the y-intercept, which means evaluate the function d at 0, and it happens that the output through d when the input is 0 is negative. So the y-intercept happens to be negative. It's right there. So it's gonna be the brown curvature. Okay. All right. So let me erase these and retain just the brown. So long story short, that's the d. That's the d. So that's d of x. Okay. So d of x is this branch and this branch. Collectively, they make up the function d. I still want to find this point, the x-intercept. So let's find it and discuss it in class. Okay. So find the x-intercept. I gave you an earlier problem like this. I mean, if I solve this for you, you know how to solve the other one. I want you to actually discover it on your own, and then we discuss it in class. For sure that guy is negative, right? You know that if you get an answer that's not negative, you're not getting the right answer. Definitely the x is negative. All right. Let's move on to, should I give you a hint? So what's the hint here? How do you find the x-intercept? To find the x-intercept, you need to find the x so that d of x is equal to 0, right? So you want this to be 0, it becomes an equation, you solve it. All right, so let's keep going. Let's move on to the next concept. Question 3, how do we obtain the graph of the function negative f of x if we know how to graph the function f of x? Okay, so let's give this guy the name g of x. So g of x is negative f of x. And if you want to continue doing what we used to do, how about instead of having x for the name of the input, how about we have a placeholder, a bullet. Okay, so g of anything is negative f of the thing. And let's say that the function f has a graph like this. Let's say this is the function f of x, and I would like to know how to graph g if g and f are intertwined via this recipe algebraically. Okay, so I would like to know how this translates at the level of geometry. Well, if you replace this bullet by a, let's say, okay, so if this bullet is a, this guy and this guy are a, so g of a is negative of f of a. Let's say a is right there. Let's say this is a. F of a, according to the picture, that's f of a, right? This is f of a, say. It should be vertical. It's not vertical. Let's say this is f of a. Correct? That's the point whose coordinates are a comma f of a. And I'm looking for the point on the graph of g whose first coordinate is a. So on the graph of g, maybe it's red, right? So on the graph of g, I'm looking for a point whose first coordinate is a. Definitely its second coordinate is g of a, right? Definitely. Because any point, by definition, any point on the graph of g has coordinates a comma g of a, where a is in the domain of f. So the a we're talking about is right there. What g is gonna produce at a is what f is the opposite of what f produced at a, right? You see the minus here? So what g is gonna produce as an output for the input a is what is the opposite of what f used to produce for input A. So I'm gonna go to f of A, and I'm gonna take the opposite, and that result is gonna be g of A. Okay, so what's f of A on the picture? That's f of A. What's the opposite of f of A? That's the opposite of f of A. Correct? That's the opposite of f of A. And what's the opposite of f of A? That's g of A. So that's g of A then. Correct? That's the point I was looking for. That's the point on the graph of g whose first coordinate is A. It's right there. And what's the relationship between this blue point and this red point? Well, the relationship is they are symmetric with respect to the x-axis. Correct? So this happens no matter what A is on the graph of f, what A is in the domain of f. So for each point on the function of f, you're gonna reflect it in the x-axis, and you're gonna create the function. You're gonna create the function g, or the graph of the function g. So long story short, the graph of g is gonna be obtained from the graph of f, but by reflecting it in the x-axis. Okay, so this is what we just discovered. So let me summarize it for you. So negative f of x, because I'm just trying to answer the question. The question didn't have g. I introduced g. It's negative f of x. So negative f of x is obtained by reflecting the graph of f, and the x-axis, right? The graph of f of x and the x-axis. Okay. All right, so let's move on to the next question. How do we now obtain the graph of the function f of negative x if we know how to graph the function f? So let's call this function h of x. First of all, let me tell you the difference between this thing, this guy, f of negative x, and negative f of x. Again, it's very similar to the discussion we had earlier between f of x plus c and f of x plus c. So over here, f is acting on x, and then the result is multiplied by -1, or taking the opposite of the result. Okay, so we're taking the opposite of the output of f. Over here, that's different. Here we're taking the opposite of the input, and then f is acting on the opposite of input. Okay, so again, the timing is reversed. So f operates after the minus kicks in. Over here in the previous one, f operates, or the minus operates after f kicks in. Okay, so h of a bullet then in this context is equal to f of the opposite of that bullet, right? This is how the recipe of h is defined. Okay? Now, if we know how to graph the function f of x, let's say that's the graph of f of x. Let's give it like something like this. Let's say this is f of x. And let's say we are interested in a point A. We are interested in a point A. So h of A is f of negative A according to the recipe. So, just based on the picture, since f is only defined on this interval, I'm gonna take A to be negative, let's say, because I want to talk about f of negative A according to where f is defined is just on this side. Anyway, so I'm looking for a point. I'm looking for a point on the graph of h whose first coordinate is a, right? Sure, the second one is h of a, but the question is, how is h of a related to f of a? Well, h of a is f of negative a. Okay? So h is gonna produce at a the same thing that f produces at the opposite of a. All right, let's see where this thing is. Where is negative a then? If this is a, negative a is gonna be right there, right? Something here. So the idea is they are symmetric with respect to 0. If this is a, that's negative a. And what's f of negative a according to the picture? That's f of negative a. This guy. It should be vertical. Probably this is vertical. So this is f of negative a, right? So this height is gonna be exactly what h is gonna produce at a. So the same height, probably here, right? So that's the height that that h is gonna produce at a. So that's h of a. So h of a is f of negative a. That's f of negative a. So h of a should be the same height. Okay? So that's the point I was looking for. That's the point whose first coordinate is a and belongs to the graph of h. So h of a. And how is it related to that blue one then? They are symmetric with respect to the y-axis. Correct? So since h is related, since this is going to happen for every point, right? For every point, so it's going to happen point by point. So you're going to be constructing points that belong to the graph of h that are symmetric to points on the graph of f with respect to the y-axis. So all in all, you're going to have the graph of h is going to be symmetric to the graph of f with respect to the y-axis. Okay? So this would be this this discussion here. So let's conclude it. So f of negative x is obtained by reflecting the graph of f right? So you're going to reflect this in the y-axis. So every point on the graph of f is going to have a symmetry with respect to the y-axis, and that symmetrical point is going to belong to the graph of h. Okay? And vice versa. So we're going to reflect the whole thing in the y-axis to obtain the graph of f of negative x, which was labeled as h of x. Okay, so let's collect these two results that we just have, or we just discovered in this theorem. It's reflections in the coordinate axes. Negative f of x, it's the very first one above that we just discussed. Negative f of x is obtained by reflecting the graph of f in the x-axis, and f of negative x is obtained by reflecting the graph of f of x in the y-axis. Okay, so let's go to the book again and do a few problems. That's on page 195. Let's do one of these problems. Use transformations. So we're going to use those transformations we learned, translations, which are shifts or reflections, to graph the function. Let's do 72. G of x is the square root of negative x minus 4. So that's on page 195, and we're gonna do 72. So we have the function g of x equals square root of minus x minus 4, correct? Okay, so we're gonna start from a parent function as usual, and clearly the parent function is going to be square root of x. So we're going to start from p of x, the parent function, which is square root of x. We know how to graph this. This is simply that's simply this graph, right? So that's the P of X. And what I want to do is I want to inject, we're going to inject this minus, which means the opposite of X. So we're going to multiply X by -1, and we're going to also inject this -4. Okay, so you do it in any order you want. As long as you do the steps correctly, you're going to find the same graph G. The easier one is to start by injecting the -4. I'm gonna do the one that probably is gonna cause confusion. I'm gonna inject this minus before I inject the -4. Okay, so let's go for the minus, which means I'm gonna inject the minus right there and create an intermediate step. Let's call this intermediate function. Let's call it I don't know, k of x. And as I promised, I'm gonna inject this minus right here, so which means I'm gonna have square root of minus x. Okay, what is k then in terms of p? Algebraically, what is k in terms of p? Well, p of anything is square root of that thing, right? I'm talking about the square root of this guy. So that's the guy who's gonna be playing the role of star now, right? So star is, that guy is -x. So p of -x then. P of -x. So one more time. P of anything is the square root of the thing. I'm talking about square root of -x. So star has to be -x. So star has to be -x. So it becomes p of -x. Okay? Alright, so k of x is equal to p of -x. That's the algebraic relationship between k and p. We know how to graph p. It's right there. Now the question, how do we graph p of -x, which is k? Well, if you know how to graph p, p of -x is obtained by reflecting the graph of p of x and the y-axis. So reflect this in the y-axis to get the function k of x, right? So reflect p in the y-axis. Okay, reflect it in the y-axis to get the function p. And if you reflect p in the y-axis, you get this, right? I'm gonna try it again. So something like this. Oops. One more time. So something like this. Okay, if you reflect it in the y-axis, that's what you get. That's k of x. Okay, so k is an intermediate function. My eye is on G, right? My eye is on G. So one more thing, I'm gonna inject this 4, right? This -4 thing. Okay, what's g of x then in terms of k? G of x is equal to, which is equal to square root of -x minus 4. And what I want is, I want an algebraic connection between G and K. An algebraic connection between G and K. Take a moment to figure that out on your own. K of anything is the square root of the opposite of the thing, right? So k of anything is the square root of the opposite of the thing. How is k related to G? Well, what should star be so that this whole thing here becomes the opposite of the star? Well, the star better be x plus 4, right? The star better be x plus 4 because of the presence of this minus. That's gonna be the opposite of the star, and that's gonna make -x -4 as we have here. Okay, so the star has to be x plus 4. So that's gonna be then k of x plus 4. Okay, so I'm gonna say it again. K of anything is the square root of the opposite of that thing. What I want to establish here is a relationship, an algebraic relationship between G and K. Well, what I have is square root of negative x minus 4. And what k produces is the square root of the opposite of the star. So who should be the star? So the opposite of the star becomes negative x minus 4. The star better be x plus 4. Observe that if you take the star to be x minus 4, then you're gonna get negative x plus 4. You're not gonna get what you have under the umbrella here. You're gonna get a different thing, right? So what I'm saying is, you might confuse this with this. Your first guess might be this because you're seeing minus 4, so you might guess, okay, I'm gonna subtract by minus 4. But look, k of x minus 4, check. K of x minus 4, the star is x minus 4. It's gonna be the square root of the opposite of that star. So it's gonna be the square root of the opposite of that star, which is x minus 4, right? The opposite of the star. The whole star is gonna be affected by that opposite. So the opposite is gonna affect everything. And that's the same as square root of negative x plus the 4, right? Plus the 4. It's not minus, so you see that the sign is not the same. So you don't get what g of x is. You actually get something else. Okay? So this is why I said at the beginning, injecting this minus before the minus 4 might cause problem. And this is what I was alluding to. The other way, if you add negative 4 before you add this opposite, it's straightforward. Okay? Try it on your own. It's very much the same as we did before. Alright, so now we know what star should be, and we established this relationship between g and k. G of x is simply k of x plus 4. Okay? Alright, now how do you graph k of x plus 4 if you know how to graph k of x? We know how to graph k of x, right? How do we graph k of x plus 4? Let me take you back to that corresponding slide or page. We're talking about this, right? K of x plus 4 is obtained by shifting the graph of k of x to the left a distance of 4 units. Agree with that? So we're gonna shift the graph of k to the left by 4 units. So we're back to this. So we're gonna shift this guy to the left by 4 units. And we're gonna obtain, actually let me write this down for you. So a g of x, which is k of x plus 4, is obtained by shifting the graph of k, which is the blue one above, the graph of k of x to the left by 4 units, right? So we're gonna shift that 4 units to the left, and we obtain what? We obtain something like this. This is 0, 0. Now we're gonna go to negative 4, 0, right? So we're gonna have, let's say something like this. That's at the point negative 4, 0, right? Make sense? Okay. All right. Obviously, this function doesn't go down. Okay, this is wrong, but you got the idea. One more time. Let's try it again. Okay, so it doesn't flatten, but it becomes, I mean, it's not as steep as it starts, okay? So it's gonna flatten, but doesn't become horizontal. Okay, again, still is not very correct, but you got the point. So this is k of x. Okay. All right. Let's now move to a different problem. How about 86? So the question for 86 is, use the graph of f given. So they gave us f, and graph this indicated function, which is this function. Okay, so they gave us f. This is f. What they want is they want this new function f of negative x plus 3. Okay, so I'm gonna take this as a picture and then take it to our notes. Let's paste it here. Okay, so this is on the same page, but now number 86. All right, so let's give this guy, as usual, a name. How about we call it a of x? Okay, so the function now we wanna graph is function who's labeled as a, and we're gonna do it as usual in steps by incorporating just one transformation at a time. We have a negative x, we have a negative, the opposite to be injected, and then a plus 3 to be injected. So we're gonna cook up from a parent function. The parent function is this one now. It's not one of these basic ones that we just discussed at the beginning of this section. They gave us a parent function, it's f, and they want this a of x to be graphed. So that's my parent function. I'm gonna build towards a by doing one transformation at a time. Let's start by, let's say, injecting this minus. Okay, let's inject this minus, and let's call this intermediate function I. So I of x is f of negative x. Okay, so I of x is f of negative x. And how do you graph f of negative x if you know how to graph f? This is f. How do you know how to graph f of negative x? Well, this is theorem 2, right? F of negative x, you just reflect the graph of f in the y-axis. So you reflect in the y-axis. Let's do it on the same graph. To obtain I, you reflect in the y-axis. So you're gonna get, this guy is gonna become this. This guy is gonna become this, right? Correct? So one more time. The coordinate of this point, let's zoom in so you can see it better. The coordinates of this point are negative 1, 0. If you reflect in the y-axis, you're gonna have 1, 0. The coordinates of this point are negative 4, negative 3. So now if you reflect in the y-axis, you're gonna have 4, negative 3, 4, negative 3, right? And you're gonna have the same curvature, but now over here, correct? So maybe, how about this point? What's that point over here? This is of coordinates negative 2, negative 3. So you're gonna go to 2, 3. So the point is here. So that point has a reflection here. That point has a reflection. That point is negative 3, negative 4. So 3, 4 is that point. So this, and the function is gonna go like that, right? Okay. So something like this. Again, it's not gonna be very accurate, obviously, but this is the idea. Okay. Who's that function? That's the function I of x. That's the function I of x. So we obtain the function I by reflecting the graph of f in the y-axis. Okay. And finally, I'm gonna add 3 to this result. So I'm gonna create a new function. You know what? Let me just write the details for you. So I of x is obtained by reflecting the graph of f and the y-axis. Okay. This is an intermediate step, and the final step, I'm after a now. I'm after a. So a of x is simply this guy, which is I of x, right? I of x plus 3. And we know how to obtain I of x plus 3 if we know how to graph I, right? This is theorem 1. So a of x, you just shift vertically by 3 units upward, right? So a of x is obtained by shifting the graph of I at distance of 3 units. Distance of 3 units upward, right? By shifting by shifting the graph of I of x upward at distance of 3 units, right? Let's do it this way. So upward at distance of 3 units. So we're gonna shift the graph of I 3 units upward. So this point, which used to be 1, 0, now it's gonna be 1, 3. So it's gonna be here. Okay, let's zoom back in. And this point, which used to be 2, -3, is gonna be 2, 3, shifting everything up by 3 units. This point, which used to be 3, -4, now it's gonna be 3, -1. And this point, which used to be 4, -3, is gonna be 4, 0 now. Okay, and then the curvature is gonna be the same as the original one. It's not gonna look the same, obviously, because I'm doing it by hand. So, but the idea is the curvature has to be the same as the blue one. It has to go through these points. Let me try again. These points that I just highlighted. Okay, so something like this. So that's the function a of x. Okay, so you could have alternatively, instead of going through the steps that we did, you could have added the 3, right? So you could have added the 3, which means you take that function, you shift it up by 3, and then to inject the minus, you reflect in the y-axis, you get this, correct? So try the other way by reversing the order. Instead of having the opposite of x first, add the 3, and then have the opposite of x. So you're gonna shift up, then reflect, as opposed to reflect, then shift up. Okay? Alright, so this is one more thing. So the last question, which I'm gonna leave as an exercise, we discuss it in class. It goes like this. If you know how to graph the function f of x, how do we obtain the graph of the opposite of f of the opposite of x? Okay, so this is gonna be left as an exercise, and we'll discuss it in class. Okay, so this ends this section.